Good morning, class. Today we are going to start a new chapter, that is that micromechanical analysis of lamina. This one is third unit. So in this case, before going to discuss, we should know some review definitions of stress, strain, elastic module, and strain energy. So these are the definitions. These are the definitions. These are the definitions you should remember. Already we are discussed in second year mechanics of solid subject. What is stress? Stress is load per stress. It is an ability of a material to resist load per unit area of cross section. This is called stress. Actually, stress is denoted by sigma, like this sigma. So the actual definition is load per unit area of cross section is called stress. And second one is strain. What is strain? It is strain. The general definition of strain is that it is the ratio of change in length to the original length. So delta L, you can write also delta L divided by L. So the delta L means change in length and a small l means original length. So it is the ratio of delta L or delta L divided by L. So next one is elastic modulus. See, elastic modulus means Young's modulus of elasticity are also called modulus of elasticity. It is denoted by E. So you know very well about stress strain diagram. So from stress strain diagram we can write stress is directly proportional to strain. Stress is directly proportional to strain. Here this one is remove and we can write a constant. Sigma is equal to capital E into small e. So this E is nothing but Young's modulus of a material or modulus of elasticity of a metal. So finally we can write E is equal to stress by strain. So these are the basic definitions of stress, strain, elastic module. Let us we'll write units also. So what is the units of stress? Newton per meter square or Newton per mm square. So what are the units of strain? So strain has no units. And what are the units of Young's modulus of materials? So capital E is equal Newton per meter square or Newton per mm square. So these see, in advanced materials, generally we are discussing about what are the different types of composites and what are the different manufacturing methods of composite materials, and also definitely we should know what are the mechanics of materials. So we need to calculate some forces and how much strain will happen inside the body and how much stress applied on your body due to application of load and how much elastic constant. So generally in problems we can take E is equal to into 10 power 5 Newton per mm square. So how it comes? So this E is constant value. So in mechanics of materials we should find this E value. So that's why we need to we need to study of those stress, strain, elastic module. These are the basics. And let us discuss introduction. Introduction of macromechanical analysis of lamina. So first of all, what is macro? Macro means a large size of molecule, and also micro means a small size of molecule. So here macro mechanical analysis means here mechanical is nothing but some forces. An analysis of lamina. So what is lamina? A lamina is a thin layer of a composite material that is generally of a thickness on the order of 0.005 inch, that is 0.125 mm. See, here lamina means a lamina is a thin layer of composite material that is generally the thickness of you know very well what is composite material. Composite material is a material which is combination of two or more materials or dissimilar metals. So here the thickness of material is the range of 0.005 inch. So that is in mm, we can say 0.125 mm. So this laminate is constructed by stacking a number of laminates in the direction of lamina thickness. So mechanical structure made of these laminates. Generally, the mechanical structures are made of these laminates. So here the laminates are size are 0.05 inch and that is in mm, 0.125 mm. So the mechanical structures, generally the structures are made by these laminates, and generally the application of mechanical structure made of these generally the general applications, leaf spring suspension system in automobile. Generally suspension system in automobile, leaf springs. So that leaf springs are made by these mechanical laminates, and so and also these are continuously subjected to varied loads such as bending and twisting. So these laminates, these mechanical laminates, the size, what the size? 0.05 inch. So the general application, the mechanical structure of laminates are leaf spring suspension system on automobile, and these are continuously subjected to the various loads, that is bending load, and this is twisting load. Twisting is nothing but torsion. Okay. And So I will now I'm going to draw a diagram for which is called as a laminate. So isentropic homogeneous. See, this is the laminate made of three laminates. See, 1, 2, 3. So this size is 0.15 mm. So these are the example of a laminate. So this is an isentropic homogeneous isotropic homogeneous matrix. That is, isotropic means the total material of this composite is same as a single unit, and the stiffness of the lamina varies from point to point depending upon whether the point is in the fiber, the matrix, or a fiber matrix interface. See here, we can find out we need to find out strength and stiffness, and also stress, strain, like that. So we can, let us say, this one is case A, and this one is one side, and this one is case B treated as other side. Let us I will discuss at one side, that is case A. Case A, subject the square plate to pure normal load, P in direction 1. So this one is direction 1 and this one is direction 2. And next one is measure the normal deformations in direction 1 and 2, that is delta 1A and delta 2A. Here the change in length at one side, section at one side, and change in length and section at other side. So next we can take a case B, apply the same pure normal load P as in case A, but now in direction 2. So the normal deformations direction 1 and 2, we can take it as 1B and delta 2B respectively. See here, we need to equate both equation. Delta 1A is equal to delta 2B, and delta 2A is equal delta 1B. So 1A is equal to 1B, 2A is equal to 2B. So unidirectional. However, taking a unidirectional square plate, the same dimensions. Unidirectional means W into W into T. Out of large composite section thickness T and conduct a same case A and B experiments, note the deformations. So these are the generalized equation of a stress strain diagram and based on Hooke's law. So let us discuss next class. We will discuss complete mathematical analysis of generalized equation of Hooke's law.